In this demo, I want to talk a little bit about Wireshark's protocol hierarchy feature, which is another statistical feature that I consider part of basic analysis because it's something I end up doing really more often than not. Now, protocol hierarchy itself is just a tool, and a tool is only valuable in the context of the questions it answers. So I want to frame this discussion through the times when I would want to use the protocol hierarchy tool. And really, those times are going to be really when I first get into a new capture and I really want to understand the lay of the land. As I mentioned before, most of the time when you go into a new packet capture, you're going to be overwhelmed with data. You're going to have a whole lot to deal with unless you had some other type of input which allowed you to query a very, very specific, maybe individual conversation, which might be the case with some security examples where you're maybe pivoting off of a security alert. But in a lot of cases, you're just going to be capturing packets from an individual system or opening a larger packet capture that's going to have a whole lot of stuff in it. So when that happens, you really need to understand the lay of the land. What are you working with? What are your initial inputs that you can use to pivot off of in order to find answers to questions you might be asking? So the protocol hierarchy window really gives you an opportunity to answer that question, to determine the lay of the land, and see the nature and makeup of a packet capture based upon the protocols that are present. Now, in this case, you'll see that I have a file open called HTTP ESPN. It's one we've looked at before, and we'll look at several more times just because it's a nice example of a few clean HTTP requests and responses. Now, what I'm going to do to pull up the protocol hierarchy window is go over here to Statistics and click Protocol Hierarchy. There aren't any options to choose. You just click Protocol Hierarchy. Now, when I open that, we're presented with this hierarchy screen, which is a little busy, but it's not too complex, so let me explain it to you. You'll see here, first of all, we have a few different columns. The most important column is the one on the left here, which describes the protocol. And what we have here is a hierarchy of the packets that exist in this capture divided into their protocol starting at the bottom of the OSI model. So you see here we have the entire packet frame here, and you see we have a percentage of packets that fall within that. So of course 100% of our packets are packets. From there we move to layer 2 and we have the Ethernet protocol. In this case 100% of the packets in this capture are also Ethernet. From there we move down another level to the network layer and we see IP listed. All of these packets are IP version 4, so we have 100% of those packets are IPv4 listed here. Now, I can actually collapse this here, and you'll see that everything else goes away because all the remaining results fall under this IPv4 section. So I've expanded it. We see we now have 2 layers, so not an individual layer, but 2 layers. Those are UDP, User Datagram Protocol, and TCP, Transmission Control Protocol, and these are our Layer 4 protocols. These are the 2 most common Layer 4 protocols, so it stands to reason these are the 2 we're going to see. Now in this case, we see that 2.9% of the packets are UDP, and 97.1% of the packets are TCP. So you can kind of see this hierarchy taking shape where we're moving up the OSI model, which is kind of counterintuitive because we're moving down on the screen, but still we're moving up on the OSI model and looking at protocols in this way. Now I can expand UDP and we see that all of the UDP packets here are DNS packets, so domain name system, which is a layer 7 protocol. So we've moved up to the application layer, which is the embedded protocol that's riding on top of UDP and IP here. So 2.9%, again, we see 2.9% is listed both for UDP and DNS because all of those are DNS packets. Now for TCP, I'll expand that, and we see the layer 7 protocol here listed as well. In this case, we see hypertext transfer protocol is responsible for 12.7% of the TCP packets that exist. Now we have an additional layer of context broken down if we expand HTTP. So you see I've contracted that and I expand it, and we see we have assets broken down by file type. So we have some PNG image files, we have some media files, JPEGs, XML, GIFs, and just text-based data as well. So we have all those different things represented, and it allows us to see not only the makeup of the protocols, but we're actually seeing the makeup of the files transferred as a part of this protocol, which is a nice little feature provided here. So we have this hierarchy, which becomes very clear in this context. This is a very simple example. And we also have the percentage of packets. Now, keep in mind, when you get down into some of these layers, you'll notice that there's not a clear distinction on where all of the packets are. So for instance, we say that 97.1% of this capture file is TCP, but we really don't see 97.1%. We don't see all those packets represented. There's 928 packets and not all of those are here. And that's because not all of those TCP packets are going to be necessarily HTTP. We may use HTTP as the control protocol to exchange files, but those files are actually being transferred across just a normal TCP data stream. So they're actually just going to report as TCP and not HTTP, which is why those percentages won't match up ever so perfectly. So basically what we're saying here is that 97.1% or 928 of these packets are TCP, and of those, 121 are HTTP. So the rest of those would just be standard TCP that may be a part of that HTTP conversation, but still in this view, they're going to report as standard HTTP and not discretely HTTP. So that may be a little confusing, but that's something to consider when you wonder why some of these numbers maybe don't match up absolutely perfectly. Now, the cool thing about this screen, like I said, is it really gives you the lay of the land. I can look at this and pretty much make some really good assumptions about what's going on in this capture. We see that we really just have HTTP data and we have DNS data. Those are the things that would both be present when we're actually browsing to a web page. A DNS request is performed to resolve a domain name to an IP address, and then an HTTP request is made to the web server at that IP address, right? So this is very simple, and you can also make a lot of decisions based upon this, or at least use this to help ask questions that will drive your decision making. Of course, we know this is an HTTP transaction to the ESPN.com website, so all the things we see here in this hierarchy stack up and they make sense. Now, I've talked about the percentage of packets column here, the packets number column here, and we can also see we have additional fields to look at in terms of the percentage of packet bytes, the number of bytes, bits per second, and so on. So we do have a couple of other useful things here. Now, in this case, we can limit this to a particular display filter. You see down here at the bottom, we see that no display filter is applied. But if we had applied one, in that case, we could actually just limit that. So as a matter of fact, let's do that. I'm going to go ahead and close this, and I'm just going to follow an individual TCP stream. So I'm just going to follow this TCP stream here. I'm going to close that window out, go back to statistics and protocol hierarchy. And notice that we're dealing with a lot less packets. So in this case, we only have 6 packets are presented, which is reflective of the filter being applied behind us here. And it shows that down below. So it says display filter TCP.stream equals 0. So we're applying that based upon the filter. So I can close this, clear out the filter, go back to protocol hierarchy, and we're back to showing the entire thing. So Wireshark doesn't make this abundantly clear when you're viewing protocol hierarchy based upon a filter. So if you say you maximize this screen and it's taking up your entire window and you can't see behind you that a filter is applied, down here at the bottom it may not be too intuitive to see that there's a display filter here. So you have to make a habit of looking for that. Otherwise you're going to be making decisions based upon some data that's representative of just a filter or a subset of data rather than the whole stream of data, and that can get you into trouble really quickly. So something to be aware of, a little trick there. Now again, this is a very simple example of using this protocol hierarchy window, and this is such a simple capture, it's not of immense value here. So let's actually get rid of this and let's look at a different example that maybe is a little bit more impactful. In this case, I've actually just fired up Wireshark and just captured a bunch of packets that I generated manually on the system I'm presenting from here. So we have a lot of stuff. In this case, we have down below, we have 16,000 packets, a little bit more than that, so a lot more. And this is going to be representative of a real world scenario where you have an individual workstation and you want to capture packets from it to troubleshoot some type of issue. So you're going to get all kinds of packets being generated, which doesn't include just the pristine packets that are part of your scenario. In the real world, you're going to have all this other stuff, and especially if you're using an operating system like Windows 10, which is notoriously really chatty and has a lot of other different protocols enabled, does a lot of phoning home, you're going to get a lot of excess packets. So starting with the protocol hierarchy is a good way to kind of get the lay of the land here as well. Now, I'm going to go ahead and open this, and I'm going to maximize it because there's a lot to be seen. And you'll see here this screen is a lot bigger, has a lot more data on it than the previous example we looked at. So we have a lot more to process and dissect. As we see here, Wireshark shows this information already fully expanded. And I think that works for some people, but I actually like to take a little bit different approach because I think it's too much data on the screen at once and it's too hard to kind of dissect what's going on. So I'm going to do something a little bit different here, and I'm going to actually contract a lot of these things. So I'm going to look at all the major protocols and shrink those back down to where we're a little bit more manageable. Because what I really want to do here is walk through the story that the protocol hierarchy is trying to tell me, because that is what it's doing. It's telling you a story of the different protocols and the different conversations going on at a very high level. And I think when everything's expanded all at once, it's a little hard to get that story, because you obviously don't read a 20-page document by laying all 20 pages out in front of you at once. You flip page by page, and I think that's an important way to look at this, and that's what I'm going to do and what I would recommend you do as well. Now, in this case, as we might expect, everything is Ethernet, so 100% of our packets are Ethernet. Now, from there, we see a couple other things we haven't seen before. Of course, we still see IPv4, we see IPv6, we see ARP, which wasn't in the last example, but of course, we would expect ARP traffic to exist on the network. And then we see some link layer discovery protocols, probably some things built into Windows, maybe some things being generated by routers, etc. Those are normal. I'm not going to worry too much about those. If you want, you can expand those. We see things like spanning tree protocol and Cisco discovery protocol, kind of inconsequential to this, and that's kind of standard chatter. Once you start doing this more, you'll start learning to filter out things that are kind of standard chatter, and we're going to talk about a few of those as we go along here, and you'll see that. But nonetheless, we're going to ignore that for now and focus on the other two network layer protocols we see, which are the ones we expect, IPv4 and IPv6. Of course, right here we see IPv6. There's very little of it going on. It looks like only 10 packets going on there. So I can expand that, and we see that 2 of those are just UDP, and 8 of those are ICMP v6. The 2 UDP packets are multicast DNS and DHCP v6. Now, if you're on a network where you don't have IPv6, where it's not supported, and you see this traffic, well, then you know you're probably on a network that does support it to some degree, and you probably want to see about disabling that or tweaking that. Never ceases to amaze me how many people will say, my network doesn't do IPv6, we've got it disabled everywhere, only to find out when they capture some packets, there's a bunch of v6 traffic floating around. So in this case, this workstation definitely is enabled for v6. It doesn't look like it was talking too much here, but we do have that. So if that's unexpected, maybe that's worth digging into. But if it's not related to the scenario at hand, maybe it's not. But nonetheless, we have that here, and we can expand that and see what the makeup of that is. Now, the rest of the capture, and really the majority of it, 99.7% of it, is IPv4. So if we're running on an IPv4 network, that's expected. Now, I can expand that and see we have 3 protocols listed here. In terms of transport layer protocols, we have UDP, which is 4.7% of the traffic, and TCP, which is 94.3% of the traffic, or a little over 15,000 packets. We also see ICMP, which is kind of one of those weird anomaly protocols that is hard to put into a specific layer. Some people would say it's kind of in between a layer 3 and 4. But nonetheless, it's displayed here now. So we see we do have some ICMP traffic here that might be of interest. ICMP is really a troubleshooting or an administrative protocol. And while it can be generated automatically by some devices for various reasons, generally anytime I see ICMP in a scenario I'm troubleshooting, I'm going to want to look at it because I want to understand where that's coming from, because it can either point me to some type of error state, maybe some packets getting dropped because of a TTL issue or something like that, or an admin who's trying to do some troubleshooting, or maybe an attacker who's getting control of a system and is trying to test connectivity. So ICMP is anomalous to me a little bit, or at least of interest to me, and something I want to know is there. So it's pretty cool that this breaks it out here and shows me that there are indeed 114 ICMP packets that I can dig into. Now, a cool thing about this window is you can actually pivot straight from it, and that's a pretty cool thing to show. So I can actually right-click ICMP here, and I can do a couple things. I can apply as a filter, so I can just filter directly to that traffic. I can also choose to find it, or I can actually colorize it. Depending upon the scenario, I'm going to do a couple different things. Normally, I'm just going to apply a filter so I can go straight to it. But again, sometimes I might just colorize the conversation so it becomes present, visibly present later when I'm scrolling through other bits of data. So you'll see here, I'll apply that as a filter. I'll go ahead and shrink this back down where it's a little smaller, and you'll see behind me here that we have ICMP here, and we see all of that traffic clear as day. And it looks like it's going on through most of the capture. The capture is about 16,000 packets, and this starts at packet 4 and is going at least through packet through 16,000 there. So this was happening most of the time, maybe all the time we were capturing. So interesting and a nice way to see that that data there. Now, the good thing here is since I've already got this protocol hierarchy open, when I pivoted to that data and applied that filter, it did not change my filter here. So no display filters applied, so it didn't change my data view. And that's good because it would be really weird if you were pivoting off this, left it open, came back to it, and the data had changed kind of without your knowing or behind your back. And that would be a little bit of a weird thing, and you wouldn't want that. But nonetheless, we have that ability here to apply filters or colorize conversations directly from this window, which is super useful. So to move past the ICMP, we still have this matter of UDP and TCP data going on. Starting with UDP, we see it's only a small portion of the traffic, 4.7%. I'll expand that, and we see we have a couple different things going on. We have Teredo, so IPv6 over UDP tunneling. That protocol exists and is going on, is at least responsible for some communication. Only 4 packets, not a lot, so probably not anything of consequence. We have some SSDP going on, which is a relic of Windows and some of the things it does. Quick, which is used by Google Chrome for some of its services, and a lot of Google services for updating. That's a really neat protocol that's interesting to look into. Multicast DNS, and of course DNS itself. DNS being one of those things that runs on UDP that we expect to see quite often. In this case, 3.8% or 614 packets are DNS, which is a lot. That's a lot of DNS requests. So probably we expect maybe there's some type of browsing going on here. We're resolving a lot of domain names, so you're going to see a lot of DNS associated with that. Particularly probably browsing a lot of sites that have a lot of embedded links into them. So like a news site, or we talked about examples of ESPN, how it has a lot of embedded content. So you're resolving a lot of names, a lot of content delivery networks, and so on. So when you see a really large percentage, like 3.8% of DNS, that's something you usually will see is a lot of web browsing and web browsing to sites like that with a lot of those embedded links. So we don't know that for sure just by looking at that, but that's a hypothesis that we could make. So that's all the UDP we have to deal with. I'm going to go ahead and collapse that back down. And then we're left with TCP, which is really the bulk of the traffic, 94.3%. So I expand that, and we have a couple of things of interest here. The two things that are probably normal are we have SSL and we have HTTP data. So we have web browsing, both occurring in an unencrypted form. So HTTP, Hypertext Transfer Protocol, unencrypted web browsing. Then we have SSL, which in this case is probably going to be HTTPS. So SSL over HTTP. Of course, we can apply a filter to that and actually look at it. And we see we have TLS data going on here. We can actually click into that and see the port it's running on if we want and learn more about that. But in this case, we have that data filtered here where we can see it and we can kind of confirm some of our thoughts. We see in this case, if we look here under TCP, Transmission Control Protocol, we see that we're talking over port 443. So this is probably HTTPS data, which makes sense given we're looking at a bunch of other HTTP data as well. Now, the other thing of interest here is we have this notice of a malformed packet. So that's a packet Wireshark wasn't entirely able to process because something was wrong. It didn't work quite right in its dissector. Some field was off. Maybe it got messed up communication. Maybe there's some type of TCP error going on. In this case, I right-clicked on that and applied a filter, and we see we have a couple of those. It says it's a spurious retransmission, and we'll talk about retransmissions later. But the cool thing is Wireshark does show you these malformed packets. So if you're having a communication issue that's maybe related to latency or a device not communicating successfully with another, maybe you're a programmer and the software you developed doesn't seem to be syncing up as it should, you can go in here and look for malformed packets really easily, and if you find those, they may be the culprit that's responsible for the issue you're dealing with, or at least a symptom of the issue you're dealing with, so you can use that to trace it back. So we see that here, and that's going to make up the bulk of these three things. SSL, HTTP, and malformed packets are going to make up the bulk of this TCP data that we're dealing with. So lots of good things here, nothing really too out of the normal. Even in normal packet captures, you're going to have some malformed packets here or there. You're going to have some protocols you don't expect, like some of the things that go on with Windows, IPv6 tunneling protocols. IPv6 itself is unexpected for a lot of people. But this let us learn a little bit about the lay of the land. I think as you're watching this, you're probably saying to yourself, okay, well, this is probably just someone doing a bunch of web browsing, maybe with a ping going on in the background, which is responsible for all that ICMP traffic. You could definitely make that assumption from what we're seeing here and what I've showed you, and that would be accurate, right? I created this scenario by getting a ping going, so just pinging 8.8.8.8 in the background constantly. I went and browsed a couple of different websites. So I browsed, I think, to to Bing, and then to CNN, and then to Google, and then I did a Google search, and all those things were happening here, and this was over just a small amount of time, maybe 20-30 seconds. So the protocol hierarchy gives us the lay of the land. It really does help us see what's going on before we actually dig into the packets, and that's one of those techniques that's really going to be super valuable to you. The ability to use the statistical features of packet analysis tools like Wireshark to make sense of a much larger data set. You can't be expected to go through 16,000 packets individually or break those down necessarily in individual conversations. You have to summarize these things, usually with some type of statistic, and then break it down from there. So if you're asking the right question and using those statistics to help you develop questions, you're definitely on the right path, and the protocol hierarchy feature is one of those tools that's really going to help you along the way there. So we'll continue to use this. There are some scenarios later on where we're going to be presented with a problem scenario and start with the protocol hierarchy and use that to figure out what are the right questions to ask to further it along. So if you have some packet captures you're dealing with or have some of the sample ones I've provided, go ahead and open the protocol hierarchy, dig through that, see what you can figure out just from that alone, and get comfortable pivoting off of this hierarchy to other packets to answer questions that you may have.